This is my Lab 2 Projectile Motion lab report. The object used in this experiment was a paper ball with a mass of 0.0046 kilograms. The object was thrown from a height of roughly a little over 1 meter above the floor. Camera was fixed during this recording, and the motion takes place entirely in a vertical plane. The object moves across the screen, does not move toward or away from the camera. In Tracker, I placed a calibration stick using a meter stick in the scene to set the scale. The x-axis was placed along that meter stick, and the origin was placed directly below the initial position of the object. The y-axis points upward. I then marked the position of the object frame by frame to obtain the x and y positions as functions of time. From the video analysis, the object follows a curved path typical of projectile motion. The horizontal motion is approximately uniform, while the vertical motion changes due to gravity. My computational models are based on the momentum principle, which states that the change in momentum of an object is equal to the net force multiplied by the change in time. Equivalently, this is Newton's second law. In the first model, the only force acting on the object is gravity. The gravitational force is downward, with magnitude equal to the mass times the gravitational field. No other forces were included in the first model. This model represents ideal projectile motion without air resistance. In the second model, I included both gravity and air resistance. The drag force always points opposite to the direction of motion and has a magnitude proportional to the square of the object's speed. The drag force is implemented by multiplying the squared speed by a proportionality constant, which we call b, and by the unit vector opposite to the velocity. The value of b was adjusted so that the predicted trajectory best matches the experimental data. When I set b equal to 0, the model automatically becomes the gravity-only model. In the simulation, arrows are used to represent the velocity of the object and the forces acting on it, including gravity and drag. These arrows update throughout the motion. The main assumptions in my model are that the object is treated as a point particle, gravity is constant, the drag force depends only on the object's speed and direction, other effects such as lift, spin, or changing air conditions are ignored, and the motion is two-dimensional. This graph on the screen shows the experimental trajectory from Tracker, the predicted trajectory from the gravity-only model, and the predicted trajectory from the gravity plus drag model. The gravity-only model overestimates how far the object travels horizontally. The model that includes air resistance closely matches the experimental trajectory, not perfectly because I did have some errors, especially near the end of motion. This shows that air resistance plays an important role in describing the real motion. Terminal velocity occurs when the net force on a falling object becomes zero. In the gravity-only model, the vertical velocity continues to increase in magnitude throughout the fall. This means the gravity-only model does not predict a terminal velocity. In the model that includes drag, the downward velocity increases at first, but then gradually approaches a constant value. This indicates that the drag force grows until it balances gravity, producing a net force close to zero. Therefore, only the model with air resistance predicts terminal velocity. If none of my models clearly showed terminal velocity during this short throw, a better experiment would be to drop the same object from a much greater height, such as from like a high balcony, so the object has more time to reach a steady falling speed. If the objects were thrown straight up with the same initial speed as my original experiment, um, uh, the object, or in the original experiment, the object has both horizontal and vertical velocity components. If the object were thrown straight up, the horizontal component would be 0, but the initial vertical component would have the same magnitude as the original vertical component. Ignoring air resistance for comparison, the time to reach the ground depends only on the vertical motion. Vertical motion with constant acceleration, the position is given by the final position equals initial position plus the initial velocity times the change in time plus 1/2 gravity times the change in time squared. The time to reach the ground is determined by the initial height and the initial vertical velocity. Since the initial vertical velocity and the initial height would be the same as in the original experiment, the time to reach the ground would be the same. The horizontal motion does not affect how long the object stays in the air. With air resistance included, the time would be slightly different, but the main conclusion remains that the vertical motion controls the flight time. Overall, in this lab, I recorded the two-dimensional motion of a real thrown object. I analyzed the motion using Tracker, built two computational models using the momentum principle, and compared the experimental trajectory to predictions from a gravity-only model and a gravity plus drag model. The comparison shows that including air resistance, produced a significantly better agreement with the observed motion. This demonstrates that real projectile motion cannot accurately be described using gravity alone.